Refracting telescopes are telescopes that have lenses. They're made for viewing objects at infinity, or at least very, very far away. The objective and the eyepiece, just like with a microscope, are both converging lenses. And the tube length is set to be equal to the sum of the focal lengths of the objective and the eyepiece. So if we have light coming from very, very far away, then the light rays that reach the objective are parallel to each other. They will intersect near the focal length of the objective, and that's where the image from the objective will appear. Then this image becomes the object for the eyepiece, and if we continue the ray diagram through the center of the eyepiece and then parallel focal point for the eyepiece, we can see that these rays will spread out from the eyepiece, and if we trace them back, we will get a magnified image, which is inverted. So if we want to figure out the angular magnification of a telescope, we can look and see what the angle is both with and without the lens. So if we look at without the lens, or without the telescope, the light rays are coming in at some angle with respect to the principal axis. And that angle is going to be equal to, if we look at this triangle here, so with this triangle here, we can see that that's going to be equal to, or roughly equal to, the image height for the objective, that objective image height divided by the focal length of the objective, since this image appears very close to the focal point of the objective lens, or at the focal point of the objective lens if the object is at infinity. So then with the eyepiece will make its own image, and then the angle that is taken up by that image, this angle here, has, if we look at the tangent of that angle, that angle is going to approximately be equal to the image height divided by the focal length of, or this image height, which is here, divided by the focal length of the eyepiece. So we're looking at this triangle here. So then if we take the ratio of those two angles, the h primes cancel out, and we get that the magnification of a refracting telescope is approximately equal to the ratio of the focal lengths of the objective and the eyepiece. Now, besides refracting telescopes, which use lenses, we can have reflecting telescopes. So reflecting telescopes have mirrors. A refracting telescope uses the lenses to collect and focus the light. The reflecting telescope uses a curved mirror. So the light comes in past this secondary mirror, and then the light that's collected by this curved mirror is focused and reflected by the secondary mirror out the side of the telescope. So this particular design, and then you have an eyepiece to look through, this particular design is known as the Newtonian reflecting telescope. Other designs are possible. Sometimes a hole is placed, instead of in the side of the telescope, in the back of the telescope to put an eyepiece or other instrument that's being used to measure the light. In this case, the secondary mirror reflects the light through the back of the telescope and into the eyepiece or other optical devices. This is known as a Cassegrain telescope. A Schmidt telescope has an additional correcting plate in the front of the telescope to correct for any spherical aberration caused by the spherical mirror. So this correcting plate does some additional correction, and you can tell that we also have here a Cassegrain setup because the light is sent through the back end of the telescope. So some telescopes are refracting telescopes that use lenses, some are reflecting telescopes that use mirrors. The refracting telescopes are very easy to make when the lenses are very small. They have really, really good magnification. So they're good at looking at bright objects that you just want to magnify. Things like birds, so using it for nature observing is a good use of a refracting telescope. Or if you want to look at the moon and planets, they're fairly bright, and the magnification allows you to see the detail on the moon, look at the craters, and look at the planets and see Saturn's rings and things like that. If you want to look at very faint objects such as galaxies or nebula, then you need to have a very large aperture to collect a lot of light. And it's way easier to make a very big mirror than it is to make a very big lens. A big lens is very heavy and hard to polish very precisely. So reflecting telescopes are good when you need a large light collecting surface. They're not as subject to chromatic aberrations, and they're best for faint objects like galaxies and nebula, and these are the telescopes that are typically used for scientific observation. So you can see a couple of large telescopes. This is an optical telescope, and this is a radio telescope that collects radio waves and makes images using radio waves. So here are the ideas that we looked at today. We looked at cameras and saw how the f number or f-stop controls the size of the aperture that the light comes through. We looked at how lenses, when you get a lens glasses prescription, they're specified by power in diopters, where you take 1 over the focal length in meters. We've also looked at a simple magnifying lens, compound microscope, and refracting telescopes, and seen how to find at least approximate expressions for all of the magnifications for these devices.